from Test Dynamics. Today I'll be presenting to you NI USRP devices. Today what I have here is an NI USRP 2920. It is a software-defined radio produced by NI and can do ranges between 50 MHz to 2.2 GHz. In this case it has two channels, one that does TX and RX and the second channel that just purely does RX. So for this demo we're going to delve into the world of spectrum occupancy. Okay, let's get into the software.
Alright, so moving on to the programming for the NI USRP. It's quite straightforward in LabVIEW. You just choose what blocks you want and go from there on how you want to capture the data. So let's start here on the left. As you can see, we initialize the USRP here. We tell it LabVIEW what IP address we want to go look at. Then we set the triggering time, and then from there we just move on to these two blocks here, which set the what was called the node properties for the USRP. So in this case we're setting the IQ rate, which will be the bandwidth we're trying to look at. We also then set which channel we are looking at. You can do this many different ways. You can have separate ways of configuring this, but for this case this is how we're going to do it. In this case active channel 0 is actually channel 1 on the device. You can set the carrier frequency as well as the gain you would like, and also the active antenna that you would like. Then there's a whole bunch of math that's going on here that we use just to display the graphs properly and correct for the data that we're pulling, but we're going to ignore that and going to focus more on actually getting the data from the USRP. He has more configuration settings for the USRP. From there we just start a session which tells the USRP that we are now looking to pull information from it. Over here we then specify what we would like from it. In this case it is a complex double output. As you can see, there's you can do single channel, multi-channel, all depends on what you really want. For this application we just purely want that. We also have a little timeout here in case the USRP freezes up for whatever reason, or there's network problems or whatever. From there then obviously this is just put into a while loop, so it will repeat itself until we tell it to stop. Once we tell it to stop, then it will close the session and then also close, effectively shut down the USRP.
Okay, so this is what we'd call the front panel in LabVIEW. Here you can see everything that you set up in the previous block diagram that I showed you. In this case, this is what the end user will be looking at the end of the day. We've set it up at the current moment to have a tab system. This will be the main page in this case, where you have the overview of the 4 graphs that we've specified. As you can see on the left here is the settings I previously discussed that we had. Number of samples, IQ rate, timeout, channel gain, etc., etc. This is just the quick way to initialize the USRP and change settings on the fly without having to go into the physical code to make those adjustments. So the IQ rate is basically the bandwidth of your USRP that you want to look at in terms of frequency range. As I mentioned earlier, we have an FM antenna, so for this demo we're going to just look at the FM range. So if I just quickly change this to 90 MHz, that will be the carrier frequency. So what the carrier frequency does, it basically sets the center frequency at which you want to look at. In this case, because we have the 20 MHz bandwidth, we'll be looking 10 MHz to the left and 10 MHz to the right of the carrier frequency. So if I press run at the top left here, we should see pretty much most of the radio stations popping up there in that range. You'll see there's quite a few ones that are a bit weak, but that's obviously might be down to the placement of my antenna. So yeah, let me just walk you through the graphs at the moment. So the top left here is the persistence graph. If we go to the tab for it, you'll see the point of this graph is just to show how frequent a frequency is there. So the frequencies that are usually transmitting for a continuous period of time will have a very defined peak and have these more red colors. But in the case where we have bursty transmissions, they will fade out over time, obviously because they're not being transmitted so frequently, which I'll show you at a later stage when we look at a different frequency. Next we move into the scrolling graph, which is personally one of my favorite graphs. This allows you to see the frequencies in a sort of a 3D graph form, so you're going to have how the waveforms change over time. And if I just pull down this lower limit a bit, you'll be able to see the peaks a lot more defined. As you can see there on the left and right there are quite a few smaller peaks marked by the lighter blue color, and then the strongest signals in green over there are obviously the frequencies we're picking up at a much stronger power rating. Moving next to the baseband power spectrum, as you can see how we've set it up that there's a few things that can be seen. So the red graph is basically the frequency in real time. As you can see, it's very jittery, it's moving around a lot. The purple line is the RMS average, so this helps you see much easier where the peaks actually are, because if you try to look at the red line, graph, you're not really going to see, oh, there's a radio station there, or there's a frequency picking up there. So this makes it a lot easier to see that. And the green section is basically the peak hold. So this allows you to see if frequencies were there at some stage. So obviously if they're not very common occurrences, they won't really affect the RMS graph, the pink line, but they will show up and sort of leave like a footprint of where they've been. So if I just press restart here, you'll see this resets itself, and you'll see some of those peaks that we had earlier are no longer there because those were obviously burst transmissions. So next, if we move over to spectrum occupancy, this basically just is a tally of how frequent a signal's been operating in our measuring time period. In this case, you can see there's quite a small peak on the left over here. That's due to it probably not always being in the lower surge limit that we set at a negative 90 decibels. So every now and then it might just pop over that and pick that up, but yeah, that's the main reason why you'll see some frequencies not being as strong as others and not occupying that frequency for a large period of time. So now if we move back here, I'm just going to quickly stop, and we're going to move over to another frequency where we have seen some bursty transmissions in the past. I'll just click run over here. I hope we can see it some today. So yes, let me just move to the scrolling graph and pull this up a bit. Doesn't appear like there is many today, unfortunately. Let me actually just move and change this to 210 megahertz and run it again. Okay, yes, there we go, that's perfect, that's exactly what I want. So if we move into the scrolling graph here, let me just pull this up. I'm not sure if you can see on the screen here on the left, just about between 206 and 207 megahertz, you will see there's obviously a frequency that's transmitting there, but alongside it, there's these small lines that are going across the screen. That's obviously a bursty transmission that's happening. It's not your typical burst transmission that you get from a cell phone or whatever. These are like pretty much instantaneous for one sampling period that we look. There's a little bit of a transmission that's being transmitted over there. But if we now look at the persistence graph where I'm showing over here, you can see it's being transmitted and then fades out. So that's the whole point of this. It shows how frequent frequency is, and you can see, oh no, it's maybe bursty, or maybe it's not always there consistently. This allows you to identify signals that might not always be there. And on the right of here, sorry, I forgot to mention this earlier, is all your settings for this, just to change the colors. But yeah, this is a fantastic case of how you can pick up these burst signals quite easily, because if you just look straight up at the baseband power spectrum, you won't necessarily always see it. If you were just looking at even the RMS value, you wouldn't be able to see that. But making use of the peak, you can see, oh, there's a bit of a bursty transmission there. Looking at the scrolling graph, you can see every now and then there's a burst transmission and what ranges it's varying between. And then also on the persistence graph, you're able to see it sort of in real time transmitting over there. So yeah, that's pretty much the use of this NI USRP for this demo, just showing how you can use it to scan your local area for any RF frequencies around. Obviously it depends on what antenna you have. In our case we only have FM, but we are able to do a bit higher frequencies. You can also use this for monitoring the GSM networks or anything else like that, in that case where you need to see, oh, is there a specific frequency that's being occupied, depending on time of day, etc., etc. So yeah, the USRP is quite a powerful device. Especially with this one, we have quite a nice bandwidth of 20 megahertz, allows you to see a lot of things at once. And there's been a lot of weird frequencies that we didn't really expect to be there that we've picked up. Like now, right there's someone bursty transmitting on that signal for no reason at all. That was quite a rare occurrence. But yeah, this is what you can do with the NI USRP. So if you guys have any questions or want us to show anything else, please let us know. Otherwise, enjoy your day.